I'm pleased to invite our next speaker, Shri Sagnik Chatterjee, IIIT-D to the stage. Please join me in welcoming him to the stage.
I hope I am audible. Okay. So this talk is actually going to be quite different from the kind of talks I'm not. This talk is going to be about quantum computing, not about hardware, not about crypto, not about QKD, but quantum computing. So to that end, I have a question for the audience. How many of you have actually taken a foundational course in quantum computing? So can I just see a show of hands? So I'm guessing most of you are like students over here. So let me ask you another question. How many of you have taken a foundational course in linear algebra, let's say undergrad linear algebra? Okay. This seems like a much easier audience to work with. Okay, great. So what I do research in is not going to be covered by this talk because I thought I would talk about something that's more accessible to a wider audience. Let's start with the slide, and I'll hope that this is a more of an interactive session. So this is a typical introduction to a quantum computing course, and raise your hand if you recognize that book on the other end. So it is recognizable, right? And I have a list of the archive clippings of most of the famous algorithms over here that we have all been exposed to at some point. The interesting thing is, if you look at the dates on these things, you'll see that the latest algorithm that you get that is covered in a quantum computing course comes out to around 2002. So therein lies my first survey question is, can you just raise your hand if you were born after the QFT algorithm was released? So is there anyone in the audience who was born after 2002? You can raise it high, there is no need to be ashamed. Okay. How many people were born after Shors and Grovers were released? I am myself one of those. Okay. So the question to you is, we have a lot of investment that is going on currently in the hardware. So if the textbook of quantum computing was released in 2000, what have researchers been doing for the last 25 years? We are still trying to implement a Shor's algorithm for like 2-digit numbers. What are we actually doing research-wise in the algorithms area? So that is the thing that we are going to be addressing in the last one. It's not a very heavy talk. It's accessible to people with a basic linear algebra background. However, there will be things that look dense. They are not actually. And I am available tonight after the lectures also. So if you want to follow up in more detail, we can talk after the lecture as well. If you have any questions, just raise your hand or just call my name out and stop me. So these are things that we can expect from this talk. So Professor Usha in the morning shared a quote that talked about this beauty of abstract mathematical models. So that's what David Mermin was talking about. I hope that you take away some of this flavor from this talk. We'll also talk about the philosophy of modern quantum algorithm design. So most applications that we see on current quantum hardware, they were developed almost 25 years ago, right? So what is the philosophy driving modern quantum algorithm research? That is something we are going to be talking about. And obviously overview of techniques. These are some of the things that we are not going to cover in this talk. Hardware details like how to implement said algorithms, I have no idea. And possibly they are beyond the reach of even most of the most powerful hardwares right now, because we'll be talking about things that require many ancilla qubits. So they are not going to be implementable in the hardware that's present today. So you can take this talk as a challenge and use your own field to advance towards this particular goalpost. I will not be covering modern research topics in other fields like quantum crypto, quantum information theory, and I will also not be giving a complete coverage of modern research topics. So it will be a very niche talk, and the talk will also not contain details because the details are mathematically heavy. It's quite late in the day. I don't want to bore all of you. So with that said, it seems like I'm not going to be talking about much at all. So you can rest easy, but don't be deceived. Okay. So just show of hands if you think that this statement is true. So I'll read the statement out if it's not visible to the web. So in a quantum algorithm or a quantum circuit, the gates that we use are necessarily unitary operators. Is this true? Raise your hands if you think this is true. You can raise your hands. I'm not going to call you personally and ask you. So if you think this is true, you are correct. It is true, and it's a consequence of the Schrodinger equation. Great. Okay. Another quantum computing 101 question. Unitary operators correspond to reversible operations. Is this true? True? Everybody raising your hand means it's true. Okay, great. And you are correct. By definition, an inverse operation should exist. Great. Now we have these two statements, right? The quantum gates are necessarily unitary, and unitary operations are reversible operations. Is this statement true? Only reversible operations can be carried out by quantum algorithm. False. Can someone give me an example why you said it false? Okay, I am not considering measurement right now. We are only talking about reaching towards these statistical ensembles at the end. So prior to measurement, does this statement hold true? Let me put it in a little bit more context. Suppose you have a quantum state, right? So I'm guessing most of us have an idea of what a quantum state is. So you can think of it as a vector in a complex valued space, right? Suppose I want to apply something that is not a rotation operation. Is that possible? So if you are confused about what I am saying, so this would appeal to people who have taken the course. You have seen that most of these operations or people talk about going forwards and backwards in time and so on and so forth. So this question actually lies at the heart of modern algorithm design. So now that my context is clear, how many of you believe that this statement is true? Show of hands. So you believe that the statement is true, that only reversible operations can be carried out. Somebody else? So all of you are guessing there is a catch in the question. That's why nobody is raising their hand. So this is false, but I regret putting the false on here. It's not necessarily true. That's the correct answer. So the gates that we will be implementing will still be reversible. So quantum circuits, unitary operators are by definition reversible. But we should stop thinking of only reversible operations as quantum operations. What do I mean when I talk about this? So this is what most applications actually go towards. So you have a Hamiltonian for a closed system. To people who have no idea what the statement means, we just talked about AI and finance, right? So financial operations. We talked about solving optimization problems. What do these things actually do under the hood? We formulate some linear programming problem or a mathematical programming problem and then use an annealer to solve it, right? So this is nothing but forming some sort of a Hamiltonian mapping. A Hamiltonian mapping is nothing but a Hermitian matrix, and then we take this Hermitian matrix, exponentiate it to get unitary gates. And this is linear algebra and quantum computing 101. However, Hamiltonians only describe closed quantum systems. Suppose I return to my earlier question. Suppose I want to evolve a quantum state without describing it as part of a closed quantum system, right? So let's say more formally, I want to apply some linear operator, not necessarily unitary. How do we apply this? Any wild suggestions from the audience? And don't feel bad if you don't get it straight away. So it's incredibly tricky to think of it, but once you see the solution, it's elegant. So if you have some idea, just like shout it out. So I want to apply a linear operator that is not unitary. How do I do it using a quantum circuit? Yes. Super operator representation. Yeah, that's great. So, okay, I'm not going to cover that in this talk, but that's great. Like a hand for him, please. That's actually a very nice thing. So one way of thinking about quantum algorithms or quantum circuits are as quantum channels. Now, once you have a quantum channel, you can think of it in terms of operators being applied to quantum channels. Great answer. However, let's lower ourselves down to like basic quantum computing. Can we take this sort of an approach and apply? And without wasting too much time, because I know I'm under a time mandate. So how do we construct a unitary corresponding to A? This is the first question that you should be asking yourself in the modern algorithmic paradigm. If you have a non-reversible operation, can you still make a unitary out of it? This lies at the heart of 25 years of research. So first technique is called augmented Hamiltonians or augmented Hermitians, whatever. What we basically do is this. So this is a superposition. I was observing this earlier. Okay. So what we do is we take that linear operator and we encode it into a Hamiltonian. So if you see, this particular matrix is again a Hamiltonian or a Hermitian in itself. It's self-adjoint, it's symmetric. Now, if you obtain a unitary by exponentiating that Hamiltonian, you essentially have a large operator, a large unitary operator that acts reversibly on a larger space. So now if you measure only the space concerning this particular, the subspace corresponding to this particular operator, and you ignore the rest of the measurements, you essentially have applied this particular operator to a quantum state. So think about this. You say that the non-reversible operation that I am going to apply to a quantum state is actually nothing but part of a larger system, a larger operator. So you apply this operator onto a larger quantum state, maybe padded with zeros. We as machine learning enthusiasts are very well familiar with padding things with zeros, right? So you pad the rest of the thing with a trivial quantum space, you apply this larger unitary, and then you measure at the end and just forget about the things that were trivially zero at the beginning. So what you have at the end is a probabilistic representation of this operator A being applied to the quantum state. This technique has many drawbacks. In fact, okay, I would like people to guess, so this seems like a very basic technique, right? Can somebody guess when this technique started getting applied, like when people thought about this technique? So this is technique number 1, we'll go up to 7. But any hazard a guess? So the first real application of this technique came in 2005. Like 5 years after Nielsen Choa was released. So because this exponential operation is computationally expensive, we should take care that this is not really a very good technique. Because now we have a larger space that we are going to exponentiate. So we address this part next, because we want to implement these operators with lower resources. So technique number 2, Suppose instead of exponentiating, if you could approximate this exponentiated unitary made out of elementary gates. Let's say if I only constrain you to use polys and just the Clifford group, let's say, can you do it? Do you think it's possible that if I give you some error parameter, can you arbitrarily approximate any unitary? You seem to agree with me? It is possible, right? Because the Clifford plus T gate is known as universal gate group. And this is actually possible very efficiently. It's efficient in the parameters that are provided to us. And there are many techniques of doing this. We will be seeing a particular technique of implementing this. And this is especially efficient when your underlying operator is sparse. Now, if you go back one slide, this Hamiltonian is quite sparse. Would you agree? It's almost empty in all the rows. So this Hamiltonian simulation technique comes in as a savior, that you don't need to necessarily exponentiate your larger Hamiltonian. You can simply approximate it out using elementary gates. So we combine these techniques 1 and 2 together to make feasible quantum circuits for a broader class of problems. Now, we go back to the drawing board, because I already mentioned earlier that encoding these operators into Hermitians were not a good idea, because at the end of the day you still have to exponentiate and then approximate, right? So, are there any other ways of doing this? No answer is a bad answer, by the way. Because these are research questions, so these are not textbook questions. So let me recap. So earlier what we did was that we know that to get a unitary circuit, unitary gate, we describe the Hamiltonian of the system and then exponentiate it, right? Now if you have a non-reversible operation, you put it inside the Hamiltonian and then exponentiate. Is there any other way of doing it? Of carrying out this non-reversible operation? So I'll give you the answer again in the interest of time. Why encode it into a Hermitian and then exponentiate? Why not encode directly into a unitary? And that took people 4 years to come up with. So 2009 was when people started talking about encoding A into a unitary operator directly. And it's an earth-shattering event, as you can see. Yes. And this is known as a block encoding. So what we do is take this operator A and we encode it into one of the blocks of a larger unitary. Now you will notice this factor alpha over here. This is just a normalizing constant, because if the norm of the matrix A is larger than 1, you cannot encode it into a larger operator and the larger operator still remains unitary. So you necessarily have to encode it by scaling it down, and these A's are just ancillars, which brings us down to the problem that we basically have to come up with some sort of a block encoding in which the A's are minimized. So these are ancillary qubits and this is the normalizing factor. And we call this an alpha A epsilon block encoding if this is true. So what this is here. So you apply UA, so you can take a photo of this and work it out on your own. What this does is, you take an ancillary register filled with zeros and you have your target quantum state at the end. You apply this larger block encoding and then you measure and post-select on the first register being 0. If it is 0, then you have applied the non-linear operator onto your desired quantum state. So this 0 is an arbitrary choice, which is very nice. This is the stepping stone to more modern quantum algorithms. Why is that so? Suppose I have a superposition of quantum states where the first register is a counter. So let's say I give you this problem. You have n non-unitary operators where the ith non-unitary operator should be applied on the ith quantum state. So you can simply have a superposition over this, where the superposition itself behaves as a counter, and when you measure and post-select on the first register being a particular counter, you have applied this operator to the ith state. So this technique is more general than what appears here. So we ideally want the number of ancilla to be small, and number of ancilla blows up if we have multiple nonlinear operators that we are trying to block and go, because they might not gel together well. So you might think that you need extra ancilla qubits for all nonlinear operators, which again ultimately defeats our purpose of having low number of qubits. However, I am not going into details, but there are techniques that allow us to reuse the ancillas. Now technique number 4, another modern quantum algorithm. Is this true? Can I apply a product of unitaries to a quantum state? Raise your hand if you think this is true. You have taken a foundational quantum course, right? A quantum circuit is just a product of unitaries, right? Okay, fine. Yeah, this is true. Is this true?
Yes.
Why is this true? So, addition or subtraction of two unitaries is not necessarily unitary, right? So, but we just saw a way of applying general linear operators. So, this is, I am building it upon the earlier thing that we saw. We know that additions or subtractions of unitaries are not necessarily unitary. But we already saw a way of applying these linear operators onto quantum states. So this is also true. However, again, the thing that I mentioned is that block encoders consume too many ancilla. So is there a better way of doing this? Obviously there is, otherwise we would not be talking about this. So this technique is called the linear combination of unitaries, and this is the last major thing I will be talking about. After that I will skip through the rest of the slides. So suppose you have the following setup. Suppose you have capital L many general linear operators which are weighed by these real valued coefficients. So you essentially have a linear combination of linear operators. And I want to construct a quantum circuit to apply this to a desired quantum state. Now, applications-wise, you can think of anything that comes under real classical computing to contain this. Machine learning, data analysis, anything. So, suppose you manage to construct these 1m epsilon block encodings of each of these general linear operators. And that is possible. Again, I leave the details up to Google. Let's prepare these two particular unitaries. So the first unitary we call prepare. So this is just a counter unitary, because you see that the register size is log of the number of operators that we are trying to apply, and this unitary basically controls the coefficients of the LCU. While the last unitary, the select unitary, is like a generalized C0 gate. Depending on the counter, it applies the block encoding onto the state. Now, how many of you are familiar with variational algorithms? QAOA, VQE. So that is your phase preparation, and this is your mixing unitary. So think about it, make the connections later. But unlike those algorithms, these are actually analyzable. And to prepare the select unitary, again we can use Hamiltonian simulation. Details I will leave up to the wind. And this is what the state actually looks like. So if you apply a prepare, select, prepare state, unitary, then you essentially end up applying this particular linear combination of unitaries to your desired quantum state. The circuit looks like this. So this register will contain your desired quantum state. And you measure here and you forget everything about here. That's all. Techniques 5, 6 and 7. So we'll combine the rest of the things into a miniature represent. Oh, it looks like an Indian flag. The colors are switched out, but okay, sure. So we will now talk about 3 very advanced techniques: quantum signal processing, qubitization and QSVT, and then we will be done. So we talked about linear transformations, right, so far. What about non-linear transformations? So non-linear transformations are also implementable for a restricted class of polynomials. So how many of you are familiar with Chebyshev polynomials? So optimization people over here. So Taylor polynomials, Taylor series. So Chebyshev polynomials are also another way of approximating. You can also go for rational approximations if you want. Rational approximations lend them very well to these non-linear transformations. So now take all of the techniques that we saw before and you now try to create block encodings of non-linear transformations. So instead of A, think about A square, where A square is not necessarily idempotent. Now, we move to qubitization. So qubitization extends this quantum signal processing technique to all polynomial transformations. So this actually, formally this talks about all Chebyshev representations, but you can extend this to all kind of flat polynomial representations. Which again brings us back to the question that, okay, are we only going to talk about these restricted kind of techniques? So the last technique applies these concepts that we have seen so far to any operator that can be, so that is a square operator. So if it has, it's not necessarily, if it can be decomposed into an SVD, which is almost all matrices, you can apply all of these techniques to this block encoding plus LCU technique to a desired quantum state. So as a recap, like applying general linear operators, applying non-linear transformations, and then combine everything using an LCU. So these are the papers. So if you see, I have highlighted the dates of most of these techniques. So I think the earliest one is 2012. This is this Hamiltonian simulation paper, and the actual implementation of these LCUs and all these other techniques. So I'll pause a bit on the slide. And I'll tell a story while people are taking pictures. So all of you know about this AX equal to B equation, right? So let's say I want to solve AX equal to B. So one of the, let's say, one of the celebrated results in quantum that is detached from Shor and Grover is this HHL algorithm. How many of you have heard of this? This Harrow-Hasidim-Lloyd algorithm. So this is at the core of all of your quantum machine learning techniques. So it basically solves a version of this AX equal to B problem. Because people wanted to solve this, this X equal to A inverse B for all general A's, all of these techniques started getting developed. Applications, I don't want to go to applications because I'm a theoretician myself, but there are theoretical applications of this as well. And for the more application minded of you, if you are interested in things like topological data analysis and things like that, I think Professor Pathak was talking about these holes in Fock states, right? So Betty number analysis and all, there, those papers are heavily dependent on these techniques that we talked about. So again, if you want to take a picture of this, or I can share the slide with you guys. Yeah. And there are many more. Yeah. Thank you. And this is like, if you want to contact me, here is my email ID. There is my website link. Yes. Thank you.
Sagnik Chatterjee, for your presentation on modern algorithmic design primitives in quantum computing. We appreciate your valuable insights and look forward to seeing how your work will influence the future of quantum computing. Now, I request Mr. Ashok Pandrapate Knowledge Associate, IIIT Group, C-DAC Pune, to kindly felicitate Shri Sagnik Chatterjee.